Hello, guys. So, looks like we made it to the end of the semester. Uh, we started this a while ago, so hopefully everyone get quite a bit of practice with Python. Uh, so, fairly large programming language, as y'all noticed, and in 16 weeks, when we want to take time and practice it and develop a good foundation in it, we stretch things out. So, obviously, there's still a whole lot more in Python we could cover, but hopefully y'all have a much better understanding of it now than when we started this semester 16 weeks ago. Last night of the semester, if you have any homework still due, please make sure you get it to me by 11:59 p.m. That's the cutoff date. I think everybody in here's had me before. That's the time when there's no longer any late submissions. That's like the class ends. So everything closes and locks at 11:59. So if there's anything left, let me know and get back in there. Just a few hours from now. So if you need me to open anything back up, send me an email or a message. And like I did really bad on this quiz, and can you open that back up so I can retake it? Yeah, that sounds. Just let me know with enough time to get it done before 11:59 p.m. to wrap it up. But gonna be kind of a short night in class tonight. One more of those odds and ends things that I wanted to cover because, well, a couple weeks ago might have been last Tuesday, maybe the Thursday before that, but we looked at multi-threading. We split our program instead of into multiple threads to run through the CPU. I kind of drew a quick picture, roughly like some starting flow chart, probably a lot more complicated than a straight line, but we would split that up into several smaller pieces that kind of run independently, so that we can jump out of our program, run these other pieces independently, and then just bring those pieces back after doing some stuff. So we have multiple things going on at once, kind of jump back and forth between them. The classic joke on multi-threading is a programmer had a problem, so we tried multi-threading. Now, problem many has the computer decides what order to work those in. Y'all might remember when we were looking at multi-threading, we did that. Keep running it and we get different results. Sometimes line breaks would be in different places or just on some print statements. And there's even on simple print statements, there was noticeable differences in how it was running. And we just split it up into multiple threads and passed each one into the CPU separately to for the CPU to carry out the work on. There's another thing that kind of follows up on that. I definitely wanted to make sure that one got included because all of the other 200 level programming classes, the Java class, the C++ class, the C# class, there's a couple others, but all of the language specific courses from 200 to 250 all have multi-threading on that list of core requirements. But for some reason, the 220 class, our class here in Python didn't, but we had that capability. So I wanted to make sure and get that because, well, the rest of the classes, I guess it's 200 to 240. All of them except 220 had multi-threading. We split it up into threads like that picture and just pass those through the CPU, which I'll do in another picture. We all have probably seen a quick representation of CPU in lectures somewhere along the way. Actually draw it as a box, right? Label it as a CPU, maybe break it up in little pieces and describe that. But that's kind of an outdated system, right? I think y'all are probably aware of that. If I pull up the numbers here on this computer in front of me, share screen and go maybe system wide. Not labeled clearly there. What about device manager? Yeah, Windows has continued their path of migrating things around. From some things have changed positions from where they were. That doesn't really have the number I was looking for either. Oh, processors, there it is. There we go. If I pull up this number, where's my little pin here? You'll notice something about the CPU that kind of makes this picture here stand out as wrong. And that's the fact that, well, they have it labeled right here. Processors is plural on most modern machines. This is a laptop I pointed out before. I run in Walmart and get the cheapest one off the shelf at Walmart, and there's not a CPU. That's something that comes plural in modern languages. Oh, did you get locked out of the room? Excuse me for 1 second. I got it. Okay. Somebody got locked down in the lab next door, so that might need to let him in, but there were people in there. So even on the cheapest laptop off the shelf at Walmart, CPU should be plural, not singular. So that is the other thing kind of connected to multi-threading that I wanted to talk about. So these rough pictures you might have seen where we just have a box labeled as a CPU, maybe some other boxes inside there with the ALU and the clock and the registers and RAM and all that labeled. But really, when we label our CPU, the box should look something more like this, right? That's the bare minimum anymore. The cheapest laptop I just pulled up at Walmart had 4 cores. And four cores isn't very, it's pretty low end these days, right? But we would have multiple processors. And it would be kind of nice to take advantage of that. Even when we did multi-threading, if we have one long program, when we load it in, the computer is just going to stick it in one of those CPUs and only one of those CPUs, and just let that run through there. And if we split that up into multi-threading, that picture I just drew there, I come out, bring that back afterwards. It's multiple threads that split up, but it's still only loaded into one CPU. It'd be nice to take advantage of all those processors or parallel processing. So that is the on and in thing that I thought would be very useful to wrap up today's class. Just look at the syntax on how we do that. Because there's another thing that multi-threading, we split it up in little pieces, feed those into CPU, and it shuffles around the order they're in. It really, the computer can still only do one thing at a time, so it jumps between them. But it's jumping between them, one CPU doing one thing at a time. But like on this cheap laptop I have from Walmart here, there's 4 CPUs, there's 4 cores. So really, we should be able to do 4 things at a time and not 1. So it'd be nice to take advantage of that, especially if we get to big things, much bigger than the one we have here. And it offers us a lot of advantages. So that's what I wanted to wrap up the class with. This is something that I think will be useful for you all at some point, and that's going to be parallel processing. I have to put my label down here because it wouldn't really fit up at the top, or I didn't leave myself enough room up there. So I'm not getting super in depth here, just looking at our syntax in Python on how to do this. How do we take advantage of having lots of cores on our machine? Y'all have all heard of parallel processing before, right? It's a fairly common thing. I assume everybody's heard of it, but so not getting in depth as far as like the hardware and how the machine does it. We just wanted to look at the Python syntax. That way, when we have a big complicated thing, like some data set with 3 million points that we fed into a pandas, I guess like spreadsheet, the tables and the tables without filters that the pandas library gives us, and then we usually use that to clean things up, and then maybe make a confusion matrix and some plot out different different comparisons from the data, lots of plots and graphs from that. But those big, huge data sets, it'd be really nice if we could take advantage of all 4 cores when we do that, or even on smaller problems. Python's the biggest problem with Python is that it's slower than a lot of our other languages. But so anything that would speed our stuff in Python up is definitely worth doing. So the module we need for this is multi-processing. And I'm going to abbreviate that because I have a feeling if I tried to type multi-processing every time we called something from that library, there would be lots and lots of typos there. So I'm going to abbreviate that. It's part of the core install, so you shouldn't have to install anything. It's part of the basic Python language itself. But when we import that, what we'll start with, let's just see how many CPUs we have, because that's a number we're going to need. Before we start splitting things up to different CPUs, we better make sure we know how many we get. So that's the first thing we want to do from this library is get our number of CPUs. So mp.cpu count. You probably would have been able to guess that before too long. CPU underscore count might not have been your first guess. When you see that name, it's probably not very far down the list. We're going to save this. Documents, delete, new folder, so I remember to put it on GitHub. Parallel, for parallel processing. I'll just call it an example. Okay, so you see here, same thing we saw from the device manager. This particular machine I'm on has 4 CPUs to work with, but on yours, I might have a few more to work with. And we're not going to get there this evening, but there's an extension here that we're not going to get to, but talking about the speed issue, I think y'all are also aware. I'll draw it really big. There's also going to be some GPUs in most modern systems as well, right? So we can split things up and use those. I'll just quickly mention it. The difference where you want to split them up is in the optimization. GPUs, like the G stands for graphics, that's usually simple calculations. The core idea of it is to turn pixels on and off. So small, simple things. CPUs are usually optimized for large, complex things, and GPU, large, complex calculations, and GPU, a few large, complex calculations, and GPUs are going to be optimized for lots of small, simple calculations. So CPUs are optimal when all your stuff is piled together, and GPUs are optimal when all your stuff is split apart. But we have lots of cores to work with. We're not going to get into GPUs this evening. We'll just look at parallel processing on CPUs. Whoops. Share my screen on this one. but that is an extension of this. We'll just look at our CPUs. So we have 4 of them to work with. So we're gonna want that number for pretty much anything we do. And well, for our case, I'm just gonna make an array, and we need a method to work with. So we do have to split it up into functions, and like we have with multi-threading, we can't just split at a random line in the middle of something. We modularize our code into functions, and then we can pass those functions. We can split up those functions amongst different CPUs. So kind of like the multi-threading picture, only instead of 1 arrow going in, we have our main and 2 other functions here in this quick one I drew, so we could feed those into 3 different cores, or some variety of that. But we can't just split it anywhere, so we do have to have functions. So I'm just gonna make a function up and like adding, and we'll just get the sum of everything. So like S starts at 0 for A, and that array we pass in, or list we pass in, S increments by that next value, and then we're returning that. So a fairly simple example, nothing complicated about that, but it'll work because we just want to look at the syntax for parallel processing. Probably don't need to print the number of cores we have. Yeah, I'm gonna go ahead and throw a message. I'm gonna go ahead and throw an error first, and then we'll fix it. Or I'm gonna throw a semi-error. It's one of those things that doesn't completely crash, but it's not quite working right either. So first thing is we have the number of CPUs, so we need to create a pool of those CPUs. We take all of our processors, our cores, that seemed like an appropriate name for it, all our CPU cores, processing cores, and we'll create a pool, which is just mp.pool. So we put them all together, and then how many do we want? Which obviously the limitation on that number is the maximum number of CPUs, which as it splits up, if it doesn't need all of them, it's not. Like if something small and 2 would be very efficient, it might only use 2. But we need to pass in the maximum number of cores we're going to use. So the easiest way to do that is just pass in that method that counts them. So that'll give us, we have a pool of, in my case, 4 CPUs, but if you're following along for your computer's own, you might have a nicer machine than the cheapest one off the shelf at Walmart with a few more cores in it. So I guess now I need an array, or a list, sorry. I'll make that for I in range 23, that sounds good. Added unappend, random.random. That's what we did. Need to import that. So import the random module. And then we'll put 23 random data points into an array. That gives us some data to work with. Nothing too fancy there. But now we need to split that up amongst our different cores. We have this pool of 4 separate processing cores on my computer. The one you're working on might have a few more. Oh, I left a big space there for a reason. I have some white space down here. So that gives us some data points, and now we need to split those up and put it somewhere. So I'm going to put This first one, I'm going to call it apply result, because we have two different ways of splitting things up. And the difference is the result we get back. So the first one is we could take that that pool of CPU cores we just put together and call the apply method. And we need three things here, or sorry, two things. The function we want to call, which is this little trivial function we made for tonight's example. That way it doesn't clutter up our example, but and when we split up into multi-threading and parallel processing, we can't just split anywhere. We have to split, we have to put our things into functions and then split them up there. So we'll call our function. And then the apply method has this args parameter. So what are the arguments we want to pass in? I'll do data first. Is that enough? Yeah, and I'll print that. So I think that's enough to go ahead and see the error message. Yep, there it is. Error messages keep coming. A really, really long one. It actually came through 25 times, 23 times is the reason. You'll see it's still coming through. Let me change that to just once. Yeah, stop that. Crash the kernel. There we go. So this was something I was going to do after I take care of that error message, but I'll come back and do that because I wanted to see the splitting it up. Well, you all saw there. I guess it covers the point. It kept sending back that error message, and what was happening is it's the args parameter, so it took that list and then passed those in as a bunch of individual values. We've seen the keyword args a couple times this semester. So it split up our list and passed it in. So I'm going to switch that to just a single element. There we go. Now we only get that error message once. Are we still getting it? But it's still passing 23 times. So I'll just stop so we can look at it. Did not stop. Okay, I'll do something else. Let me I'll just pass in one value. That's apparently still going to give us 23 messages. There we go. Did the error message stop this time? Okay, only one time that time, so we can read it. There we go. Why is that not scrolling? Okay, that's can't seem to pull up the error message I was wanting to show you all. What was that? Well, this is just being kind of annoying here. Okay, well, never mind about that error message. I'll tell you all what it said instead. I don't know why that's continually going through. It should have only come through one time there. But for some reason, our function would not stop running. But the error message it was giving was saying that it wasn't finished doing stuff. Maybe we can kind of get it. There we go. You can see the preview there briefly is you see the guard statement, right? If main equals main, then freeze underscore support. Basically, it's saying we have to. This has to be in the guard statement. We can't just put parallel processing anywhere because if we have a bunch of different files that we collect together, remember the one we actually push the run button on, or double click in the file explorer, or have our batch file shortcut start up, that file gets renamed as main. So we want to make sure we only assign our main parallel processing. We never want to accidentally assign side scripts to run in the parallel processing. So, so if name is equal to main, regard we've all seen it. We've seen that a few times. It's good for them to do that. We have to make sure only our main is splitting up to multiple processors, because bad things could happen if we accidentally split multiple files up to several processors at the same time. They might not come back together correctly. They would be fine synchronous, but there is a difference there. So when we do it this way, so here's that array thing. It needs one argument to be taken in. So when we split up to parallel processing, it does iterate through our stuff. We can't pass in single values. So even if we have a list that we want to pass in, we need to wrap that in angle brackets to make it a list containing a single list, because the nature of parallel processing does have to iterate through something. And it has to be in the guard statement. So that's the two error messages I wanted. The main two. Do I have any others in my notes? I seem to be thinking of three things, but I only made two notes to myself. I only put two things in the notes. Those are the two that made it into my notes, but for some reason I'm thinking three. So apply takes in the args, it iterates through there, passes things in one at a time, finds this sum, then puts them back together, and then puts the result into a variable that we can work with. Another way we can do this is a map result, a map. So I'm going to make another one called map result. Again, just quickly looking at the syntax tonight, all the same thing. And this time it just takes in, oh, whoops. I didn't want to do apply. I just did apply. I want to do map. And you can see on the predictive thing there, we want the function and an iterable. So instead of passing in the R to try to make a split set up into separate values, we want the function and then something we can iterate through. But we get that, have that same issue. Adding, if I put data here and print map result. So that can run. You can see it's still split it up. So when it got to the, it tried to pass things in one at a time. So both of any of our parallel processing, even if we only have a single value, or if we have a list, if we have a huge massive collection, they always need an extra set of square brackets around them for the parallel process, the parallel stuff to loop through, the map or the apply. Both of those have to loop through, iterate through something. And even if it's something that is already iterable, like a list, we still always need extra square brackets. And that's about the most confusing thing about actually writing our code. That's our two methods for doing that synchronously. Notice how we were able to get those results and put them somewhere. Synchronous parallel processing. There's another way we can pass things into the CPU. We don't necessarily have to do them all at the same time in a certain order. Oh, I never ran that or fixed it there. And there's the difference between map and apply. Notice that apply gave us back a value, and map gave us back a list. So apply gives us back a single value, and map gives us back a list the same size as we passed in. I guess my example is not good with that. If we would have had two lists that we passed in there, then that list we got back as a result would have two elements. So however many things we pass in, we get that many things back inside the list with a map. But otherwise, in general, we get the same number. And if we had really good timers set up, we would see a big difference over just running that function directly, because instead of running through that loop 23 times, it split it up amongst 4 CPUs, so that each CPU only had to run, I guess that doesn't come out even, 6 times. One of them ran a little bit less. But instead of one CPU running 23 times, 4 CPUs ran 6 times, and we got to get the same number. So we can get a whole lot of speed back, which is the biggest problem with Python. But that's not the only way we can pass things in. Asynchronous parallel processing. Is along with that, we could also just do it asynchronously. Time doesn't matter as long as it gets done. Time doesn't matter, the order doesn't matter. It is completely separate. We're just going to pass that off. Right. So if we have 4 CPUs, instead of this multi-threading picture where we pass them all in at once, instead of this picture where we have a couple things and we pass it all in at once, we'll take our main and then we'll put that on a CPU, put these over into a different CPU, and eventually we're not really too concerned about when, we'll bring those back together. They can run at the same time, they can run at different times. If they can be split up to where it's okay to run at different times, then we can run them asynchronously and get even better performance, because we can continue doing something else while the computer does that over on the side. And our syntax for that is really easy still. We have that pool of the CPUs available on our machine, which we have a method to count the maximum number we have available, and we have to pass in a maximum number to use, so we might as well use that. Count the maximum number available. Again, so that gives us all the CPUs, a big pool of those to use. And then we can do apply async, call our method. It's an extension of async, so we have the args thing again. And the difference is we can't put that in a value. Why don't I do that first? We can. Let me put it in a value to show you what we get. Async results is that, and then print those. So it doesn't crash if we do. So you can see it's kind of like a function, what we get when we just put a function name without the parentheses. It tells us that stuff's stored there. If we look up at our variable explorer up there at the top, we can see it. It has something there. Says it's the same size as the other results. So it must be just a number, but it's a little odd to access. And that's because we did it asynchronously. The order didn't matter. The sequence didn't matter. The computer just carried out the steps. So it hasn't been reassembled back to the final result. So what we need is we need a callback function that puts those together. So I'm gonna come up here and define another function. I'm gonna take this variable name. Got that. And then we'll just call this instruction to run. And what we need to do with it is pass it into a callback function. So we'll create another function up here. I'll just call it collect results. And we'll pass in some result. Because that's the problem. It found all of the answers. We asked it to add up all of these values in this array. So it did that. But it did it asynchronously. Each one was done separately, independent of the others. And the pieces of the answer are scattered all over our system. So we need another method to put those back together. So I'm going to create an array with global scope. Space that. So our async results variable, the thing we're going to print at the end, it just starts as an empty list. And then each time through, we'll just append the next thing to those results. And it's a list with global scope, so we don't have to return anything. Hopefully that made sense. We did it asynchronously. Everything was done independent, completely unaware, disconnected, remote from everything else as it was done. So after all those pieces were done, we just had random data, random bits scattered all over 4 different CPUs. So we need a place to put them back together. So that weird looking multiprocessing.pool.apply result object. It's just a bunch of bits scattered around RAM. So what we have to do is make a list of those bits, and then it will automatically turn that list of bits back into actual data that can be processed. So we have bits scattered all over our CPU. We have to put them back together in an organized fashion, which a list is a nice organized place to put all those bits, and then it becomes our data thingy, our piece of data again. Hopefully that made sense. That's a critical part of asynchronous multi-threading. But you'll notice that it's just empty. Anybody have a guess on why that is still just empty? So when we do it asynchronous, it goes off to the side. It's remote. It's disconnected from our main, at least temporarily. So our main here can continue doing other stuff. So as soon as it passed that stuff off to the other processes, it jumped to the next line and tried to print it. But there's no result there because the asynchronous processes haven't finished running yet. So before that, we do have to bring them back together. Those two lines make sure that we're all the way finished. The cores.close, that it's like closing a file, only on the closing the CPU. When everything is done, like when we write to a file, we take all our data, put it in the file, and then closing it means we're done writing data to the file. Same thing with reading it. Same thing with CPU cores. When we send all our stuff over there for processing, we send it there and then we close it. It means we're done with it. So the computer's gonna take a little bit longer. So after passing all that stuff on, now our next instruction here, our next instruction this time is to wait for that stuff to come back. So obviously we could do a lot of stuff between there. Wait till CPUs are done. And apply the result. Apply the results scattered around the various cores. So join brings our stuff back in. So kind of want to do both of those lines. We can get by with one or the other, but it's best form to do both, and it's not hard to type the two lines together. So now and we could do lots of stuff here. Could do lots of other things here while the function processes asynchronously. Oh, I just realized I left something out. So let me take a step back, comment those out, and actually call that callback function. So callback equals, what do I call it? Oh, collect results. That was a good name for it. So yeah, when I actually remember to put the callback function in there, you see we still get that empty list if we just print it. So now if I uncomment those things that I just spent a bunch of time talking about, you can see it's able to, it gets the same number. But it made optimal use of the fact that we have multiple processing cores on our machine. To effectively have parallel processors, multiple CPUs combined into one central one CPU in our modern world is what would have been considered several CPUs 30 years ago, 20 years ago. Parallel processing was around back in the 90s. So it's been around for a long time. We don't have to go all the way back to the 70s before we get to where there was only one. So only one CPU. We have to go back a ways to get there. But it gets us a lot more power. So that comment that goes in between those two lines, as we look at just the core syntax here, we could keep doing other stuff while the computer goes and does those things asynchronously in the background. Or synchronously, we can just split it up evenly. I'm going to change that 23 to a 24 so that the math works out. So on my machine, there's 4 cores. So instead of the regular type of Python script where we have 24 data points, so we send 24 elements over to a processor that's going to run 24 times to get all the way through that loop. We'll just have 4 processors run 6 times each and get the same result if we do it synchronously. Then asynchronously, we're just going to split it up and it's going to run whenever on whichever processor is available. And a whole lot of stuff going on in the background, but it's completely separate from us. That's why we have to have a callback function to put the results back together, because after the asynchronous one is finished, we don't really have data. We have bits scattered around all of our CPUs and RAM and registers and all sorts of different places. We have to put them back together, which we can just take all those bits, put them in a list, and then we have data. But that's the basic part of parallel processing. There's some other ones. Star map is a nice one, and we don't have regular map on asynchronous. We have to use star map, but I wanted to kind of keep it simple, and I was actually thinking I would be done about 7 minutes ago. I was planning on going to about 20 till. But that's the basic idea for parallel processing. As always, I'll put it on the GitHub repository for this class shortly afterwards. Does anybody have any questions about that? Definitely a powerful tool that I wanted to include because I think you all will need it. And hopefully, you know a little bit more about Python now than you did 16 weeks ago. So I guess that kind of wraps it up for us tonight. We have an hour left in our scheduled time. As always, I'll be available to answer those questions till then. I won't be doing anything except waiting for you to ask questions until then. You can ask me questions anytime. Keep my contact information around, even after you graduate. If I can help, I will be happy to. So keep my contact information around. You can ask me questions anytime. Otherwise, that was it for the class. Anybody have any questions? Okay, I assume the silence means no questions. So y'all have a great summer. It's been a pleasure having you in class, and I hope to see you around somewhere.
You have a great summer.